continue to rely on that information. It makes life a lot more manageable, so that we're not flipping the script and saying, okay, forget all the things, forget everything you think you know. It's more like, no, there's some things that you know that are still valid, and that's all fine. All right. The one additional fact that we're going to need to take into account is F equals ma. All right. Newton's second law, for force equals mass times acceleration. All right. So anytime we have a force problem, you might have to involve something like that. So there's some examples here. This is the last page of this packet. So in number one, it says find the force acting on a 2 kilogram ball moving in a circular path of radius 3 with a period of rotation being 3.7 seconds. Now, I got a little sneaky here. I threw in a recall knowing full well that I never really introduced it, the equation of a circle in this form. It's just kind of trying to slip one by you, but really, if you think about it, they're cosine and sine functions. Sometimes cosine and sine functions have more going on than just a coefficient, an amplitude. Sometimes there's a frequency. Sometimes there's a phase shift. Sometimes there's a vertical translation. All right. In this case, we're being given a periodic relationship. All right. So here is something that you should recall, that the graph of a trig function has a period equal to 2 pi divided by b. Right? So when they tell us that the force acting on the ball, we'll worry about that later. That's the F equals ma part. All right? But when they're saying that we have a period of rotation of 3.7 seconds, they're telling us the period of this function. Right? So indirectly, they're telling us that 3.7 is equal to 2 pi divided by b, which means that b is equal to 2 pi divided by 3.7. All right. Now, they didn't say anything about a phase shift or vertical translation, so the C and the D's are going to be irrelevant. They did tell us the radius is 3, so that's our A values, our set of A's. All right. That they would have to explicitly state in the problem that there's a phase shift or a vertical translation. Not typical, at least a vertical translation. It is possible to be a phase shift, but very, very rare. So my model here, R of t, would be equal to A, you know what A is, 3 cosine 2 pi over 3.7 t, comma 3 sine of 2 pi over 3.7 t. All right, so that's the model we're working off of. And that really is the only thing that's going to make, or not make anything, but it's the only thing that's weird about this. All right, because every other time we tackle these problems, anything involving a circle, it was just, oh, well, what's the radius? Slap it on there. What we're dealing with here is a relationship that allows for different rates of motion around a circle. It's almost like parameterizing in terms of a different variable. All right. But what I would need to do, so this is position. I need to figure out acceleration, right? And the reason I need to figure out acceleration is because they're asking for force. Force equals mass times acceleration. So I need to get the acceleration so that I can multiply it by the mass and determine the force. So in order to do that, I need the first derivative, r prime of t, going to use a little bit of chain rule here. So -3 times the sine of all that business inside times the derivative of all that business inside, right? So the short version is it's going to be -3 times 2 pi over 3.7 sine of 2 pi over 3.7 t. And then all that stuff again, just positive and with a cosine. Now, you can simplify, but it ends up really not being worth it, because we got to find the next derivative, you know. So the derivative of the derivative, giving us acceleration. But right now we're at velocity. Now this is the velocity vector. If I wanted to find the actual velocity, I'd have to find the magnitude of this vector. All right, so just something to keep in mind. All right, same idea with the acceleration. One thing gives you the vector, the other gives you the actual value. We need the actual value. All right, so my second derivative, sines become cosines, cosines become negative sines. That part's fine. The -3 is going to stay put. We're going to introduce a negative for the second part. But when we take the derivative of the inner function, we're going to get another 2 pi over 3.7. So we're looking at -3 times 2 pi over 3.7 squared times cosine of 2 pi over 3.7 t. Then all that stuff again, cosine becomes negative sine, except, like I said, you're going to get a sine in the middle. Not really in the middle, you know, like in the midst of the expression. Right, so that's my acceleration. So now in the final step, or final, like finale, I guess, the series of steps to bring this to a close, what I would need to do is find its magnitude. Get rid of this. Find the magnitude of this vector, or this acceleration vector anyway. And then once I do that, I can multiply that by the force, and I'll have, oh, sorry, multiply it by the mass, and then I'll have the force. All right, so you just got to kind of grin and bear it, because the magnitude of acceleration, even though it's actually not challenging, it is a little daunting to look at. Right, because what we'd essentially be doing is squaring each part, including the trig functions. And that part, it actually makes it nice. All right, so we're going to take this, we're going to square. We're going to add to it the other guy squared. And we'll slap a radical over the whole shibiggity bang. So we have common factors that can be pulled out. It's just you don't always see it until after you do a little bit of work, but the little bit of work is really just that. So it'd be 9, you got the 2 pi over 3.7 now to the 4th power, and then cosine squared of 2 pi over 3.7 t. plus all the same stuff again, just with a sine instead of a cosine. Kind of took off on me. Ooh, that is not a radical. I can't circle it in. A little bit better. All right. So when you factor out the 9 and the 2 pi over 3.7 to the 4th, you'd be factoring it out of the whole thing and taking the square root. All right. So you'd be looking at 3 times 2 pi over 3.7, that quantity squared. And that whole thing would be multiplied by cosine squared 2 pi over 3.7 t plus, I never changed my cosine into a sine. Plus sine squared of the same stuff under the radical, but cosine squared plus sine squared, regardless of what's contained within the functions, as long as they're the same, is going to cancel to a 1. So I'm really just left with that 3 times 2 pi over 3.7 squared. That is the acceleration value. Now I just need the force. So F equals ma is going to be the mass, which is 2 kilograms, multiplied by this expression. Now, the units that go along with that, they told us it moves in a circular path of radius 3 meters with a period of rotation being 3.7 seconds. So meters per second. That would be for velocity. Now, this is for acceleration, the meters per second squared. So we'd be looking at 6 times 2 pi over 3.7 squared kilograms times meters per second squared. Now, if you don't know that that's a Newton, then that's fine. But if you do know that that's a Newton, then you can just write Newton. All right. And in terms of your final answer, I mean, there's a pi in there, a pi squared. It ain't going to be pretty. Right? I mean, if you want to get a decimal equivalent just for your own purposes, that's fine. But I don't need it. Like, I'll just show you real quick. It'd be like 17.3 newtons. Good to know, I guess. The simplest fractional form is the preferred, though. Even with the decimal in it, it's perfectly fine. Right. The remaining problems are things that, like, if we have the luxury of time, I'd get to, but we don't, so we're not gonna. So that's where we're gonna end the unit. I'll stop the recording.